All right, hello everyone. I hope people have been enjoying the conference so far, and I'm pleased to introduce our next speaker, Jason Shipman. He's a huge fan of writing simple code and enjoys rethinking the architecture of Haskell applications. In this talk, he'll be talking about thread index storage. And please save your questions for the Q&A session. This talk is packed with a bunch of information. Without further ado, here's Jason.
Thanks so much for the intro, Trevor. Alrighty, so I have a ton of material to run through, so we're just going to dive on into it. So we'll be talking, in this talk, we'll be talking about the context package, context library. And we'll specifically try to answer a couple main questions. First, just what is the context library? What's the interface like? And then we'll spend most of the talk kind of thinking about ways we can apply the context library with some real examples. And if there's interest in the Q&A, we can kind of dive into how it works under the hood. All right, so for what the context library is all about, there's kind of four main facets to the interface. The core, like the bread and butter of the whole thing, is providing thread index storage around arbitrary context values. These context values can be nested to like arbitrary depth, and at any point, the calling thread can ask for their currently registered context. And then the final piece to the interface is context propagation, like to child threads. And the child there is in quotes just because Haskell doesn't have an explicit parent-child relationship between threads. But all I mean there is, thread A builds up some context, and then it starts up thread B. We can propagate that context from thread A to thread B. All right, so we'll look at each one of these points in more detail here. So to start things off with the core of the whole thing, with thread index storage, what that means is that we have a shared place where we can read from and write to by the threads in our application. And so to do this, the core type in context is a store. The store type is parametrically polymorphic, so we can store context values of whatever specific type we're interested in putting in the store. And to acquire a store in the first place, we can use this with non-empty store function. There's a couple other variants, but for now, we'll just kind of focus on with non-empty store. And with non-empty store expects a default context value and then a callback, and then we'll give that callback a store to work with for the duration of this action. So we have a way to acquire a store. Now we need a way to put context into the store to register context, and that's where the use function comes into play. So the use function, what it does is we give it a store, and we give it a context value, and then an action. And then on behalf of the calling thread, for the duration of this provided action, we'll register this context in the store. So we can kind of get an example going here, seeing the interface that we've seen so far. So we'll work with this thing type here. It's a record where it has a single stuff field and stuff as an integer. And then in main, first order of business is to acquire a non-empty store. So we acquire a non-empty store, and we give the default value here, thing with stuff set to 0. We get our store out, and then we register some context here through use, where we register thing with stuff set to 1. And so the next point is being able to nest context values. And this isn't going to use anything new. We're just going to rely on that same use function, just subsequent applications of use. And so what nesting means here is that we can override a thread's current context in a subsequent interaction. And then once that interaction completes, the thread's current context reverts back to whatever it was registered as before, if there was any explicitly registered context. And so that's what we're seeing here. So we see our first application of use, where we say, thing stuff set to 1. Then we have a kind of nested application of use where we have thing with stuff set to 2. So we can put context into our store. We can acquire a store in the first place, but it's not really any good if we can't pull context back out of the store. And so that's where the mine function and some of the variants come into play. And we'll focus on mine and mines for the purposes of today. And so mine is the main function there. You give it a store, and then it provides back the calling thread's currently registered context. And then mines is the exact same thing, just it also allows providing a selector function, so you can kind of drill into a particular piece that you care about in your context value. So we can kind of keep our example going here, where we acquire a non-empty store, thing with stuff set to 0, a couple applications of use, and then within this this innermost block here, within this innermost use where we registered thing with stuff set to 2, when we ask for the calling thread's currently registered context, we get back that thing with stuff set to 2. And then once this block completes, the current thread's context rolls back to whatever it was set to before. So when we ask for context at this point, at this line of code, we're going to have this first application. We're in that first block of use. So we're going to get back thing with stuff set to 1. And this is demonstrating that minds variant here, where we're adding the selector function to just drill into the field that we care about. So this is going to be the integer 1. All right, so how about if we try to ask for context before we've explicitly registered any through use? That's what we're showing here. Everything below here is the exact same as before. Just right after we acquired our store up on this line, we ask for context. And so because we created a non-empty store, this default context value that we gave here is relevant to all threads. So if a thread doesn't have explicitly registered context and it asks for context, it'll get back this default value. And so on this line here, it's going to be thing with stuff set to 0. All right, so the last kind of facet of context interface is around propagation. And so we haven't seen anything multi-threaded so far. It's all been single main thread. So what happens if we are on a parent thread, on the main thread, and then we build up some context, and then we fork a child thread? What's the context situation like there? And so that's what we're showing in this example. On the main thread, we use a thing value with stuff set to 1. And then from that main thread, we spin up a child thread, air quotes child thread. And then that child thread, the first thing it does is it also asks for context. And so it's not going to have any explicitly registered context of its own. So it's going to get back that default context value. So it's going to get back thing with stuff set to 0. So there was no context propagation there. If we want to have context propagation, there's a few ways we can slice that. One way is to do it ourselves. So here you can imagine a case where like your parent thread builds up some context. It takes a lot of effort to do, a lot of work, and there's no reason that the child thread shouldn't also have access to that context. And so that's what we're showing here in this example. Like we did a whole bunch of imaginary work where we built up a thing value, a stuff set to 1, registered that context on the main thread, and then on the child thread, we also explicitly registered that context. So that's kind of like the functional elbow grease, just passing the values around manually approach. But we can also let context do it for us. So that's what we're showing in this example here. So, main thread registers thing with stuff set to 1. And then on this line, instead of using control.concurrents fork.io, we use a context wrapper for fork.io that behind the scenes kind of handles the context propagation for us. And then in the first line of this child thread, asking for context here is going to have that thing 1 context that the main thread had instead of the default value. And the little asterisk here just kind of saying, like, should we have to think about context propagation? Depending upon your use case, no, but also you may really want to be thinking about context propagation, or you may want to disable it entirely. And we'll see a concrete case or concrete example of when you don't want propagation at all later on in the talk. Okay, so that was the rapid fire crash course into context interface. And so the rest of the talk, I want to spend time looking into how we can actually apply it, kind of in a more real world point of view. All right, so the 3 examples that we're going to take a look at, the first, resource sharing, and then the last one will be some servant tidiness or some servant fun that we can use context for. All right, so for the first example, the hierarchical logging one, hierarchical logging is a really fancy way of just saying you want to name sections of code. So this is kind of some example output here. We have this root name of main, and then a log message, and then we have within main we have this kind of init section, and then a DB section, and so on. So it's when you have like a root name to start with, and then any kind of subsequent names that you apply kind of inherit the name of the enclosing chunk. And so we can kind of lean on context to do pretty much all the work for us in this example. So we'll start with some imports here, some text and just bringing in context itself. But our logger type will be a wrapper around a context store. And instead of storing the kind of really contrived thing value with stuff fields and that kind of thing, we're storing logging functions. So a logging function is going from text to IO, and then we can acquire a logger to work with in the first place through this with standard out logger function. So with standard out logger is going to take a text for the root name. So in our example, this would be main. And then it'll take a callback where the callback will be given a logger to work with. And under the hood, all we're doing is just delegating to context with non-empty store, and then calling the callback with a logger wrap store. And the default value that we're saying, this is the default context value that's relevant to all threads, is this logging function we're building here. And this logging function internally is going to delegate straight to text put string line. And then this is the text the user wants to log, and we just do a little bit of careful prefixing here, where we prefix the message the user wants to log with the root name. But now we have a way to acquire a logger, and the next piece is we could write a function to log a message. And so that'll be the log function. So the log function is going to take in a logger. It's going to take in some text the user wishes to log, and it'll log that text. And internally, what it's doing is it's asking for the current or the calling thread's currently registered context through mine, which the context that we're storing here is logging function. So we pull out the logging function, and then we directly apply the logging function with the text the user wants to log. And again, we just do a little bit of careful prefixing where we say, okay, we'll put a colon before the text they want to log, just so we can kind of delineate between the name portion of the message and the actual message text itself. All right, so we can kind of get the example rolling here with our interface so far. We have a way to acquire the standard out logger. We gave the logger a root name of main, and then we can log a couple messages. And so, if we log Nido program is starting up, what will actually be printed is main : Nido program is starting up. And so the last piece that we need is a way to name sections of code. And so that's where this named function is going to come in. So named is going to take in a logger, and it's going to take in the text for that name, and then an action to run. And so for the duration of this action, we're going to give that action the name that was specified. And so under the hood, we delegate to this context function we haven't seen yet, context.adjust, but adjust is implemented in terms of things we have seen. It's implemented in terms of mines and use. But the implementation of this is not super critical. The point is, adjust kind of lets us in one shot, like one line, do a context transformation. That's where we can take the currently registered context, transform it, and then use that for a subsequent action. And so the transformation that we're applying here is this toNamed function, where we're taking a logging function and producing a new logging function. So this logging function is going to be the currently registered logging function, and then to build a new one, first thing we're going to have to take in is some text, and then we delegate to whatever the currently registered one is, and then log the text the user wants to log. And just like our previous couple examples, we're just careful to do some prefixing where we put a dot here and then the name that was specified for this section of code, just to help delineate between the name stuff and the actual message text. And with those pieces, we're all set. So we can, if we wanted to log something like this, where we have main, init, db, and so on. Here we have this app section where app is doing some stuff on a separate thread, and the thread inherited the logging function to work with, that kind of thing. We can do that with a program like this. But I won't kind of drill super far into this, but just for the high level, we have this standard out logger with a root name of main. So everything within this block is going to be prefixed by main, the entire block. And then here we have an inner block where we named it init. And so everything in here is going to be named main.init, and so on. All right, so that's our hierarchical logging example using context. Now we'll jump to the next example, which will be around resource sharing. So this one's going to take some effort to kind of build up to the point where we actually want resource sharing in the first place. And the resource we'll be attempting to share is a database connection, like a Postgres connection. So we have some Postgres related imports and a resource pool related import, not super critical. But here's kind of the types and the functions we'll be working with. So we have this user type, this user key type, a talk type, and a talk key type. And and then a couple of functions that add these things to the database. We have add user and add talk. And both of our database functions take in connection pools as arguments. And they're the first order of business in both of these functions is to acquire a connection from the pool and then go off and do imaginary database things. So we can use this interface kind of like in this example here. So this is just some preamble of like loading in a Postgres config and building a connection pool. But the important bit is down here where we're calling add user and calling add talk. So we call add user connection pool. We add Simon Peyton Jones and we add his talk as well. And so this is okay, but like a core problem with this is that there's no way for us to really, without doing some gnarly hacks, there's not really a nice way for us to share the same database connection across the calls to add user and the call to add talk. And this is really, really important if you want to run both of these operations in the same transaction. So having this problem, we can approach it in a handful of ways. One of them, kind of like the easiest one, would be to add some kind of internal functions alongside our database functions. So we have this add user prime variant, and we have this add talk prime variant, and both of these functions take in a connection, like a specific connection explicitly, instead of taking in a connection pool. And then the higher level functions that operate with pools internally just grab a connection from the pool and then delegate to the internal function. And so this is okay. I mean, this is an okay solution. It's nice in that as the caller, if we do need to run a add user and add talk operation in the same transaction, we can drill in and reach for the internal functions instead of the higher level ones. But it kind of quickly becomes hard to maintain because we have to maintain two sets of functions, and all we really care about is the core functionality of one of those functions. So thankfully we can do better than this. So that's what we're seeing here in this next example, where instead of having two sets of separate functions or having functions that take in pools, here we just updated add user and add talk to basically abstract over the pool entirely. So instead of taking in a connection pool, we're now taking in connection acquiring functions. That's what we're seeing here. But internally, they kind of behave the same as they were behaving before, where they acquire a connection from the function they were given and then go off and do database things. So this is a really nice solution in that it kind of brings the power to the caller to share the connection when they choose to. So we'll start by porting our example, our main example, back over without any sharing. That's what we're seeing here. So we grab the with resource function off of the connection pool. We call that with con, and then we pass that into both add user and add talk. And there's no sharing happening right now, but we can update this example to share if we'd like to. That's what we're seeing here. So as the caller, we grab a database connection, and then instead of passing the with con function to both add user and add talk, we pass this function where the connection is fixed. And add user and add talk they're totally oblivious to this. They're just working with the function they're given to acquire connection. But we as the caller are empowered now to share this connection. Run these things in the same transaction. So it kind of seems like we've solved the connection sharing problem without context, but there's more to it. So a lot of times, if we have our kind of user DB, like our user database related functions and our talk database related functions, we'll kind of group these functions together. And whether it's, I'm showing here like a record of functions approach, it could be a type class or whatever. But we group these functions together, and then we may close over the connection acquiring function. And that's what we're seeing here with this make user DB. So we close over the connection acquiring function, so we don't have to continuously pass it every time we want to call one of these functions. So we kind of pass it once at startup, and then we can use our user DB implementation or our talk DB implementation without really thinking about the pool or the connection acquiring function and so on. And these function definitions, they work the same way. They take the connection acquiring function they were given, grab a connection, and go do database things. And this is the kind of corresponding update for the talk DB side. So this is nice and kind of like a isolated components of functionality point of view. We have this user DB interface and this talk DB interface and that kind of thing. But it puts us right back to square one, where if we're doing this kind of stuff at startup, where we're grabbing this connection acquiring function from the pool, passing it to our make user DB and our make talk DB, then once we get down in here, like further and further into our application, there's no way for us to share the connection because the connection acquiring function has been fixed at startup. And so probably no surprise, but we can address this problem with context. So the way we'll tackle this one is we'll kind of create a general purpose resource provider type. So the resource provider type is going to be a new type wrapper around a store. And users of this provider type won't have to know that context is used under the hood or anything. That's why it'll be opaque and stuff. But so it'll be a context store where the values that we're storing are resource acquiring functions. So that's what we're seeing here. To kind of establish or to acquire a provider in the first place, we can use this with provider function. And the first thing we have to give that is a resource acquiring function. And this is meant to be the kind of like the base or the default resource acquiring function that's relevant to all threads. And then we give it a callback where we can have a provider to work with for the duration of this action and so on. And just like with the logger example, all we're doing under the hood is delegating to a store acquisition function, if you want to call it that. But so we're using this kind of lower level with store function instead of with non-empty store. And this just as library authors gives us a little more fine-grained control over our store. So here in this second parameter, we're specifying the default that we were given, the default resource acquiring function we were given. And so this has the same effect as using with non-empty store. So it makes the store non-empty. And then this second parameter here is what lets us control the propagation behavior. So here in this case, we're saying no propagation. And the reason why we're disabling propagation is that this provider, it's dealing with scarce resources, and we really, really don't want resources to be shared implicitly across thread boundaries. So we just say we're not dealing with that, just no propagation whatsoever. All right, and so now we're just going to need a couple functions to work with the provider, and we'll be all set. So we have this with resource function, which is a direct analog to data.pools with resource. So we take in a provider, and we take in a callback that will give the resource, as the provider will give the resource for the duration of this action. And we'll take a look at the implementation here. This is going straight to context.mine. So this is asking for the calling thread's currently registered context, which is a resource acquiring function. So we pull that out here, and then we apply that function with the callback that we were given. And the final piece to this kind of resource sharing puzzle is this share resource function. So share resource is going to take in a provider, and it's going to take in a specific resource we'd like to share and an action. And so for the duration of this action, we're going to share this resource we were given. And when I say share, what I mean is that any subsequent calls to with resource within this action will return the shared resource. And so internally, what we're doing here is registering context for the calling thread through use. And we're using the same trick before where the function we're giving here is a function where the resource is fixed. And so that's what lets us share it. So we can port our kind of running example over to using providers. So we have this make user DB and make talk DB. They're taking in providers now. And then internally, they work the same way. They just grab a connection from the provider, and then they go off and do database things. And so if we port our kind of integration example of these components, here at the main, like we're grabbing the withcon function here, which is pools with resource. We say that pools with resource is our default resource acquiring function, our default connection acquiring function that's relevant to all threads. This gives us a connection provider to work with. And then when we can build up our user DB and talk DB, where we provide this connection provider there. And then here we call the functions, just like we were doing before. And so this is not using the share resource stuff, but we can easily port this example over to share the connection. And that's what we're seeing here. So here, as the caller, first we build up user DB and talk DB and so on. But as the caller here, we can explicitly grab a connection from the pool, and then we can call share resource. And so the way share resource works, for the duration of this block, the resource is shared. So add user and add talk, they're just working with the provider. They're totally oblivious to any changes that might have been made to the provider. But we kind of, in a thread safe way, can share this same database connection across both the calls. And this is really, really nice for running things in transactions and so on. And the final piece I'll say on this example is just kind of like, what about reader T and local? And so local definitely could be used for something very similar. We could use local to kind of locally override a particular resource requiring function if we were storing that in the reader, or like monad reader, or whatever the equivalent type class we were using is. But the reality is it's a lot of times not so simple. You can imagine where maybe you have one team working on the user DB stuff and another team working on the talk DB stuff. Then you go to integrate those components later, and unless both teams are kind of in complete agreement on like development approaches, monad stacks, and all this stuff, that can be a little challenging to integrate them. Like if one side is using a more reader approach and the other side isn't. So this kind of resource sharing example works at the lowest common thing between them both, which is IO. All right, so the last example we'll jump into here is around some servant tidiness or some servant fun that we can use context for. So being super familiar with servant is not super critical. It will be helpful to be a little familiar with why middlewares, but I'll try to explain everything as we go. So this is a servant API definition here. If you haven't worked with servant before, the gist of it is that you can define your API at the type level. So you can define a type level API description and then do all sorts of cool things with that API description. And so this is kind of like a sample CRUD Haskell love API where we can create an attendee, we can retrieve an attendee, we can create a Haskell love talk, and so on. You can imagine a whole bunch more endpoints to work with there. And so we have this servant API definition going, and then alongside it, maybe we're building out a service interface. So we have kind of corresponding functions for our API definitions. So we have new attendee, get attendee, new talk, and so on. And a particular implementation of this service interface will be kind of the backbone of our HTTP server. So things are going pretty smooth. We're adding endpoints left and right, but we get to a point and realize that we don't have any authentication, any authorization, or nothing. So our endpoints are totally wide open. And how are we supposed to address this? There's a handful of ways we can approach this. One of which would be going into our API definition and adding an auth header all over the place. So here we have an auth header type definition here. We say the header is required. The name of the header is authorization. And then the value is some JOT bytes. I'm just using JOTs as an example, but not super critical. And then for all of our endpoints, we go in and say, you must have an auth header. You must have an auth header, and so on. And to be fair to servant, you don't have to put your particular thing you're concerned about in every single endpoint. You can just do it at a higher level and then say apply this to all the endpoints. It just fit better on the slide to kind of put it in line in these three endpoints. That's why I'm doing it this way. But the effect is the same. We've basically said all of our endpoints are going to expect an auth header. And then we go over to our service interface and start saying, okay, well, our service interface is now also going to have to accept this auth header's value type, which is these JOT bytes. So we have to attendee, get attendee, new talk, and so on to all take in this parameter. And this is just kind of sad. Like the JOT bytes value is something we expect all of our endpoints to have access to. And it just kind of seems a shame to have to bake it into the servant API and bake it into our service interface and so on. And on top of all of that, like it's putting the onus on our endpoints themselves to both authenticate and authorize the request. It'd be nice if we could move the authentication up to a higher level in the stack, and then our endpoints only have to worry about authorizing the request. And so why the web application interface package has a partial solution for this particular problem, which is it's kind of a combination of a middleware and a vault. And so if you haven't worked with Y a lot before, it's not super critical, but the gist is Y has this application type, which a lot of times we run on a warp server. And then it has this middleware type, which lets you kind of transform an application into a new application. But really the point of middleware is being able to kind of transparently inject behavior into a Y application without changing the core guts of the server itself. So you can go in and write a middleware to do some request processing when the request first makes its way into the server, but before it's actually made its way into a particular endpoint, you can do some processing in there and kind of transparently inject some behavior that you need. So we're gonna take advantage of that by writing a middleware to do authentication, and then we'll see how we're using the vault as we dive into this implementation. Vault is not something that's Y specific. It just happens to be used in the Y request type. So our vaulter is going to vault middleware is taking in this parameterized vault key, where the type parameter is JOT claims, and we'll see how we use this here in a bit. But the first order of business in our middleware is to look at the request's headers to see if there's an authorization header. If there's not an authorization header, we immediately fail authentication. And if there is, then we grab the bytes from that header and we try and authenticate. And so this is just like a dummy authenticate function where we have this the bytes that we're taking in, and presumably if we can authenticate, maybe we can get some claims info about the requester to work with. So that's what the authenticate function is doing. And then this is kind of where the sneakiness or the sneakiness comes in. So what we're doing is every Y request has this vault field on it, and it's not a very commonly used field, but the vault data structure, or the vault type, is this kind of interesting type where as long as you have a key that is parameterized by a particular type, you can put values of that particular type into the store. And so the store itself is managing heterogeneous types inside. Not super important for our example. We can just think of the vault as a place for us to put stuff on the request. And that's what we're doing here. So we grab the vault off of the request and we insert the JOT claims we pulled after doing authentication. And then we update the request to have that new vault. And then this line down here lets the request go through, to back into the warp stuff, back into the servant stuff, to eventually land in our particular endpoint handler that's supposed to process that request. So this is a really kind of sneaky communication mechanism between a middleware and a particular endpoint, because we can do some processing, get some information, stick it in the vault, lose control, and then we regain control back in our endpoint handler, and we can pull that information that we stored in the vault out. So this kind of partially solves the problems that we have. It lets us move the authentication up higher in the server stack, and it lets us pass kind of like some resulting requester or user information that we pulled from doing authentication into our endpoints. But the problem is we still have to update the servant API definition to take in a vault everywhere, just like we were doing with the auth header kind of thing. We have to update it to take in the vault. Then we have to go and update our service interface to also take in a vault. And this one is really painful because the service interface, it's unfortunate to have to marry the service interface to this very specific, Y request kind of behavior, Y request and middleware and vault behavior, because we could potentially use the service interface for like a DB only implementation, or like a in-memory kind of test server implementation, that kind of thing. It's unfortunate to have to marry it so closely to a very, very particular HTTP server implementation. So probably no surprise, but we can clean this up with context. So we'll use a very similar technique or approach to the middleware and vault combo, but instead of using a vault, we'll use a context store. So here's our add JOT claims middleware, where we're taking in a context store, and the things that we're storing in this context store are JOT claims, just requester kind of info. And so it proceeds very similarly to how our other example worked, where we look up the authorization header. If there is no header, we immediately fill authentication. And then if there is an authorization header, we grab the bytes from that, try and authenticate. And if we're able to get the claims info out, like the authentication was successful, then we register context. So we register context in the store we were given, where we're registering those JOT claims. And then the interaction that we're specifying here is the rest of the request processing. So this will, it's just like before, it'll let the request go through and into the warp and servant stuff to eventually make its way into our endpoint. And this may not seem like a whole lot, but this one context.use line is extremely, really, really powerful. Because if we think about how warp runs things, this is kind of assuming we're all running our applications on warp for web stuff. Typically, warp is what's used. But the way warp works is when a request comes into warp, warp spins up a separate thread specific to processing that request. And so one of the first things that happens when it's processing that request is it runs the middlewares. So we land in this code, and then on that thread, we register context, but then we lose control. We lose total control of that thread until the the warp and the servant stuff basically routes it into the particular endpoint that it's supposed to get to. But once it gets to that endpoint, we regain control. And the important piece is that it's on the same thread. And so this is a pretty powerful technique that's not specific to middlewares. It's really like any kind of situation where you have control of a thread and then temporarily lose control and regain it later. Because we can take advantage of that first chunk of time where we do have control to register some context, and then use that context, work with that context later on once we regain control. And so this is a pretty nice solution, because the API definition and our service interface, they go totally untouched. But our very, very specific HTTP server implementation of our service interface now implicitly has access to the claims info that it needs, like to do authorization, for example. And that's what we're seeing here. Here we've kind of converted our creation of this service, like with this make IO server, where we give it the same context store the middleware is working with, and then internally in all the implementation functions, we can grab the claims info that was specific to that request that came in. And some trivia on this particular kind of combination of a middleware and a context store. This is what inspired the development of context. It wasn't around authorization headers, but it was a similar case at work. All right, so we had the rapid fire crash course, the context interface, and then 3 concrete examples. And now to bring the talk to a close, while context from a Haskell point of view certainly isn't everything, my hope is that this talk has convinced you that it kind of opens up new ways, like some new doors to how we can write Haskell applications and write Haskell libraries. And thank you all for checking out my talk, and thanks to Haskell Love for having me as a speaker. I'll see you all in the Q&A.
Thank you so much. And you can, once again, you can join him in the Q&A Zoom link.